Good evening. I'm Dick Meserve, the president of the Carnegie Institution, and I'd like to welcome you all to a Capital Science Evening. The history of astronomy is a history of receding horizons. So wrote Carnegie astronomer Edwin Hubble nearly 75 years ago. With his discovery that the universe is expanding, Hubble revolutionized astronomy and broadened and deepened our understanding. Today, our knowledge of the universe seems to have no bounds. We have peered nearly to the beginning of space and time. We know where to place the Earth and the Milky Way in a rough map of the universe. We understand basic mechanisms of star formation and galaxy evolution. Yet, we still have no definitive answers to some of the most basic of questions. How did the universe begin? What happened in the instant of creation? What is the fate of the universe? Added to these are the mysteries surrounding dark matter and dark energy, discoveries that were unknown to science until recently, yet make up 95% of our universe. At the heart of these questions is the intimate relationship between cosmology and particle physics, between the very large and the very small. Understanding this relationship requires a wide array of tools and a multidisciplinary approach, an approach that is evident in our event tonight. This evening, for the first time, we host not one speaker, but three. In holding this event during African American History Month, we also recognize and honor the achievements of three African American theoretical physicists, Jim Gates, Herman White, and Larry Gladney, who stand at the cusp of a new understanding of the universe. These three, friends, colleagues, and opera lovers, call themselves the Three Cosmic Tenors. Dr. Sylvester James Gates is a pioneer in the development of string theory, especially supersymmetry. When supersymmetry was the first, his thesis on supersymmetry was the first MIT thesis ever to discuss the topic. And the book he co-authored in 1984 was the first comprehensive book on the subject. Schooled at MIT, Harvard, and Caltech, Dr. Gates is currently the John S. Toll Professor of Physics and Director for the Center for String and Particle Theory at their nearby University of Maryland. He also does research at the MIT Center of Theoretical Physics. Dr. Gates is the author of over 200 research papers and a popular guest on the PBS NOVA series. He is the recipient of the American Physical Society's Edward A. Boucher Award, as well as MIT's Martin Luther King Jr. Leadership Award. He is a past president of the National Society of Black Physicists and the recipient of a Public Understanding of Science and Technology Award from the American Association for the Advancement of Science. In 2009, Dr. Gates was appointed to the President's Council of Advisors on Science and Technology, otherwise known as PCAST. Dr. Herman B. White, Jr. is a physicist well known for his work in particle physics. His name is associated with a scientific equation, an equation he developed early in his career to calculate neutrino fluxes in high-energy particle interactions. After receiving degrees from Michigan State, Florida State, and Yale Universities, Dr. White joined the Fermi National Accelerator Laboratory in Batavia, Illinois, where today he is a senior scientist. In this capacity, he has helped design, commission, and analyze data from many important particle physics experiments. Dr. White is an Illinois Research Corridor Fellow and adjunct professor of physics at North Central College in Naperville, Illinois, where he also serves as vice chairman of the Board of Trustees. He is a recipient of the 2010 Edward A. Boucher Award, and he has served on advisory panels for the U.S. Department of Energy, the National Science Foundation, NASA, and the National Academies. Dr. Larry Gladney is the Edmund J. and Louise W. Kahn Professor for Faculty Excellence and Chair of the Department of Physics and Astronomy at the University of Pennsylvania. He is also the Director and Principal Investigator of the Penn Science Teacher Institute, which offers advanced education for science teachers in middle school and high school. Dr. Gladney is a graduate of Northwestern and Stanford universities. He focuses his research on basic connections among matter energy, space, and time. Most recently, he has been involved in the planning and simulation of a future space-based mission, the Joint Dark Energy Mission, to understand the origin and nature of dark energy. Dr. Gladney has served on numerous scientific advisory committees. He received an Outstanding Community Service Award from the Black Graduate and Professional Students Association in recognition of his dedication to community service. He also received the American Physical Society's Boucher Award. So all three of our speakers tonight have received that award. Our three speakers are notable not only for their dedication to science, but also for their dedication to education and public service. Just 4 months ago, they were here in Washington as invitees of the U.S. Department of Energy to speak about their work and careers to middle school and high school students at the Science and Engineering Festival. Tonight, the Three Cosmic Tenors are back to present a concert in 3 arrangements. Please join me in welcoming Jim Gates, Herman White, and Larry Gladney.
Good evening. It's a great pleasure to be back here at the Carnegie Institution. Dick and I were reminiscing a few moments ago about my last occasion to be here, which was about 7-8 years ago. It's nice to see such a full audience. We're going to try to have a little bit of fun tonight. People often think that the words physics and fun should not appear in the same sentence, but we're going to try to disabuse at least this audience of that notion tonight. And the images that you're running behind me, we will come back to. So let's get started on this little adventure. Well, what's this about? Well, in some sense, this is one of the reasons why we physicists are permitted to exist at all. Maxwell wrote these 4 equations, and the equations are amazing because they said something that no one had ever thought, which is, in this animation, I have imagined there's an electron here. I wave it around. You see the hair waving with it, the green lines. Those represent electrical field lines. And before Maxwell wrote his equations, no one had ever known that if you take a charge and batteries and some magnets and you do something, you can create a little bundle of electromagnetic energy that goes flowing away through space. And yet, we sure know what to do with that today. The equations also tell us about a strange property called polarization. We see it here winding around. Polarization actually comes in 2 different varieties, so it can wind around in the other sense. And all of this new information about light comes from these equations. What do we do with this kind of stuff? Well, we do this with our stuff. We transform society. We get telephones, we get cell phones, we get computers, we get flat panel displays, TVs. And all of that goes back to the fundamental discovery about the nature of electromagnetic behavior in our universe. And so in some sense, I think this is perhaps the first great contribution that physics makes to society, the power to transform society because of the new technologies that come out of studying equations as a way to view the world. Darwin once said, with mathematics, it seems one is endowed with something like a new sense. And those of us who work on theoretical physics always attempt to use that mathematical sense as a way of looking at the universe. For example, Einstein was the first person to know how big an atom is. It comes out of his 1904 work, not on special relativity, but on Brownian motion. And then his lens for answering that question was mathematics. So he gives us equations that tell us that space and time, instead of being a grid that one can see here, actually is flexible. It flexes and bends, and time can be made to slow down, lengths can contract. And it all comes out of the equations that we see at the top of the transparency. It's a mathematical way of viewing the universe. But of course, this mathematical way has both a bright and dark side. Out of these same equations come the information that energy and mass can be transmuted to each other, with a tremendous result that, A, we learn how to make nuclear weapons, but we also have a way of generating clean, relatively clean power, which I have a suspicion in the long term of our species' hopeful survival, that we're probably going to get back to using nuclear energy as one of the ways to solve the energy crisis. Einstein also tells us that space and time actually flexes in a different way and gives rise to the notion that gravity can be a wave. He tells us that the universe was created in a big bang, and there are people here in the audience that could tell you much more about that, so I won't bore you. But the universe starts with an equation, and I really love the story of this equation because Einstein writes this equation after a great struggle of about 8 years. And when he first writes the equation, he doesn't include this term because at that time it was thought that the universe was static. And so he goes back and, like any bright student, learns how to master an extremely technical piece of mathematics called a fudge factor. And so he inserts this fudge factor into his equation so that his equations will then agree with the view of the universe that it was static and eternal. In the introduction, Hubble's name was mentioned. And Hubble was the astronomer who first really got us to thinking about the fact that the universe is actually a dynamical place. And so Einstein, in his great genius, goes back and erases this term from his equation and calls it the biggest blunder of his career. And it stayed erased until about 15 years ago, when we have now reinstated it, but for a purpose that Einstein never thought about. We look at the universe with satellites that not only orbit the Earth, but actually orbit around points in the orbit about Earth, an L3 point. There's a satellite out there right now, the Wilkinson Microwave Anisotropy Probe, WMAP, which is busy looking at the radiation from the beginning of the universe. It's an amazing accomplishment. And from this, we get pictures that evolve like this, as we've shown here to the right. Back in '65, the then known as 3-degree radiation was discovered by accident, as so much in science occurs in accident. In 1972, we launched a satellite called COBE, which gives us a better view of this radiation, and then WMAP, which sort of is an improvement yet. And when I point at this figure, I know for this audience I don't have to say this, but I give lots of talks to the general public. And this particular image I like to refer to as a fossil. You know, people in our society have lots of discussions about the beginning of the universe. And one of the things that people no longer argue about is the existence of dinosaurs. Well, dinosaurs, part of the reason is no longer an argument is because you can go to a museum, almost any place, and point to those bones. And if someone says, well, I don't believe in dinosaurs, you say, well, explain to me what that was, right? Well, you see, this acts as a fossil that tells us physicists that we live in a universe that began in a big bang and went through a phase where it creates this snapshot of itself when it was about 300,000 years old. This is a picture of our universe as a baby. It's clever enough to have taken its own picture, and we can now detect it. We look at gravity waves through, well, what are gravity waves? Well, stars are large stars, and here we represent a binary neutron system, generate waves of gravity that can move through the universe. And we hope to be able to detect them quite soon because these two facilities I'm showing here are LIGO, the Laser Interferometry Gravitational Wave Observatory, are in operation. And the whole purpose of these is to detect these waves of gravity. We can look at the universe at different scales. We physicists have created something called relativistic quantum field theory. It allows us to talk about things that are submolecular. Here we see a proton where we're trying to extract one of the particles that exists inside the proton called a quark, but we never quite succeed. In fact, we get 2 bundles of nuclear energy, matter, out of that. Quantum mechanics says the universe is a really bizarre place. In classical mechanics, we have nice smooth curves. Quantum mechanics says that's just an approximation of what goes on for electrons. They tend to move in very jagged paths, and the most that you can say is that there's a probability for all possible paths. They also give us very strange things. The classical picture of a ball rolling down the side of a bowl says that if you release the ball at the same place at the same time, it always travels in the same path. If we put quantum mechanics in this, you get something weird. The balls released from the same place can go in many, many different places. In fact, some of them, even though gravity is attempting to pull them to the bottom, never actually fall out. This is a physicist's notion of an anomaly. It turns out that an anomaly is something we can see in our mathematics, and if anomalies existed, charge would not be conserved. But charge is conserved in our world, and therefore we use this as a requirement to fix our equations. A guy named Richard Feynman told us how to understand forces with pictures like this. These are called Fineman Diagrams. And again, it's all mathematics, but the wonderful thing about the mathematics that we physicists use is that it has beautiful pictures, that we can even go out and tell non-physicists about the story behind the equations. Feynman's story is more complicated than the picture that you just saw. He says that two electrons can repel each other by doing something funny on the side, or that the particles of light which transmit the repulsion can do funny stuff in the middle. Now, these pictures are actually calculations, and if you had a course with me in relativistic quantum field theory, like some of you in the audience have had, I could actually sit down and bore you for 45 minutes with each of these. And yet, these equations give us the most accurate information we have about nature. There's a property of the electron that says it behaves like a magnet. We've been testing this property over and over again for the last 60 years. And with our experiments, we find out that this property of magnetism can be characterized by this number. We have an uncertainty in that because that's a hallmark of science, that you have to quantify what you don't know as well as what you do. And yet, when we theorists come along with our funny Fineman diagrams, if we take hundreds and hundreds and hundreds of them, we then find out that we get this number. And this is the best understood number and agreement in all of science, where we have an experimental test, and you can see how many digits here look like those down here. And this is a purely theoretical construct. So when we physicists say quantum mechanics is real, this is the reason why we say it. We have the experiments to prove it. Let me move ahead a bit here. We just probe the structure, and I'm going to briefly touch on this because my colleague Herman White is likely to come back to this. We know that protons, in fact, have these things called quarks that we saw earlier inside of them. The electron has a friend, is a part of a family, and all of this is part of the probing of physics that we have equations which principally tell us how to get to. Let's continue down in size. For the last 15 to 20 years, a crazy group of us have been pursuing something called string theory. Now, is it science yet? Not yet. It's mathematics. It won't be science until we can get an observable prediction that someone can go into the laboratory and match with our equations. But it's the best attempt to understand how quantum mechanics and gravity go together. It's all about equations. Strings are these tiny filaments. It's often said that they're that they are pure energy, but that's not the right way to think of a string. In fact, a string, energy is made of a string, not vice versa. If string theory is correct, they are the fundamental authors of reality. They can either be open or closed. A closed string, if we think of an open string as a piece of spaghetti, then clearly a closed string is a spaghetti-o. They can move and vibrate in very complicated ways, and depending on how they vibrate, we think maybe it's an electron, maybe it's a particle of light, maybe it's a graviton, but it's all the string performing different vibratory motions. And it's all about equations, folks. We keep modifying our equations to try to get mathematical formula, and this is one representing something called a superstring, which is why you see the big red S in the middle, where we combines the property of strings with spin. In 1984, it was realized by John Schwartz and Michael Green that this idea of strings need to have the kind of spin as the electron. So they constructed this new spinning string. Shortly thereafter, they wrote some equations, and boy, it's all about equations, folks. I keep saying this. These are the equations that describe the superstring of Schwartz and Green. But in 1984 also, an event happened at Princeton. 4 people, Emil Martinick, Ryan Rohm, Jeff Harvey, and David Gross, wrote a new set of equations. And these new set of equations were unlike anything that we had ever seen before because they predicted that the string has parts that spin and behave in different ways. And when you combine them in a certain way to cancel the anomaly, which turns out to be a very special condition, you had the first definitive proof that Einstein's idea of a unified field theory was actually achievable. That set off a hysterical rage in 1984, and that's when string theory sort of burst into consciousness of physicists in general, and shortly thereafter to the general public. The equations that you're actually seeing above, interesting enough, are my equations. When I talk to young people, I like to try to get them to understand that science is not what you see in the books. If you think science is what's in science books, that's like walking into a sculptor's studio, looking down at the floor, walking out the side, and then thinking that sculptors are people who make little pebbles. you've missed the entire point of the exercise. In science, it's not the facts that we uncover that constitutes science. It's the process by which we uncover those facts. And this is something that we need to be more effectively adept at teaching our young people as they enter school. I'm going to skip ahead. Again, there's possibly new forms of matter. In our universe, we've seen all of these. And again, Herman White is going to talk about accelerators. There's an accelerator in operation right now called the supercollider. And roughly speaking, about half of the forms of matter and energy that are predicted by our equations we've never seen. And part of the purpose of the supercollider is to see this other half. Let me give you a new perspective. Because in about 11 minutes, I've done about 700 years worth of physics. I'm going to end by talk about my own work for the last year or so. I've been doing something very weird. Here's some funny pictures on the right-hand side of this. And my claim is that I can get the equations of physics by looking at pictures like this. It's almost like a child's game. Now, these pictures have to have special properties. You have to count the number of nodes in special ways and color the directions. But if you do it right, I have proofs that I can get the equations of physics out of this. I've never seen anything like this before. And by the way, at the end, we're going to see that this is a crazy idea. So these are the equations associated with this picture. And it will take me a long time to explain why these equations come up from the picture, but they do. There's a different set of equations from this picture. And this set of equations represented by this last picture is interesting because it contains Maxwell's equations, the equations from which we began our discussion of the charge moving. So, is this physics? Not quite. It's almost physics. It smells like physics. This is what we call super physics. It's got to include that missing half until the LHC comes along and tells us that those super partners are out there. This is pure mathematics. And yet, let me move past the naming of this. These are the kinds of equations that come from these pictures. I hope no one runs out of the room screaming bloody murder. I'm going to end with a discovery that we've recently made. This is a picture of that leads to Maxwell's equations. And we're going to do some operations. We're going to fold it up and put it in a box. And each of the operations that you see here is actually a piece of algebra or calculus at work, because these pictures that I show you really are equations. So if you do certain things to the equations, you're actually manipulating it by the pictures. It's a visual technique for looking at equations. And so now we're doing some integrals. As you see, we change the heights of these objects. By the way, the black balls represent what we physicists call fermions. The white balls are bosons. That's a necessary property of supersymmetry, that you have both. And now you can see that there's two sub-lattices that, in fact, look the same. We're going to jam them together. And when we do, we're going to find something interesting. Since they're identical, we're going to do a full twist with a half gainer here. And now we're going to put them together so that black balls go to black, white to white, blue lines to solid blue lines, dash blue lines to dash blue lines, dash red to dash red, solid red to solid reds. And then we get this image that I'm going to open up here. This object that I'm showing you, in fact, contains not the equations of Maxwell's, but the equations of Dirac. And so we have this graphical, weird little mathematical device that seems to capture the equations of physics. One of the really weird things about this is that this folding process is governed by computer codes. In other words, the same kinds of codes that make your browsers work are in fact governing how you fold these objects together. And so it may be that computer codes have something very deeply to do with reality. This is an idea that John Wheeler proposed some time ago. And when I first heard it, I thought he was crazy. Richard Fineman went on to explain to us that a lot of people thought John Wheeler was crazy. But also, Richard Fineman explains to us that John Wheeler's craziness leads to things like Nobel Prizes, because Fineman used one of them to get a Nobel Prize. And so, when I first heard the idea, I thought it was insane. But now, after about 27 years as a physicist, I find out that I have a crazy idea. So I've concluded if you continue to do physics long enough, you too can become insane. Thank you. Was that pretty good?
Thank you, Jim. See, I have to drive this computer. They take your PhD if you can't do it. And where am I, Jim? There I am. Okay. Outstanding. Well, good evening, and I'm really very pleased to be here tonight. And I want to personally thank the people from this organization for having us here. I was in Chicago the last couple of days, and in my house, completely snowed in, literally. So I just got here a few hours ago. I wanted to give you a brief and really condensed presentation about the way in which we actually experience some of the research that we do to test some of the equations that my colleague just talked about. One of the things that we actually have to do when we come up with ideas with regard to particle physics is to actually do experiments that test the details of those experiments, the details of the equations, the details of the theory, and try to understand, in fact, if it's consistent with nature, because the reproduction of our observation is, in fact, the definition of what we consider to be truth. There are great moments in physics, and you've heard of a number of them from Jim. The composition of the universe and searching for structure is one of the things that we actually are able to do using some of the instrumentation. Now, I'm basically going to talk to you about the things that we can do on planet Earth, the things that we actually need to be able to do these examinations. We have three frontiers today in terms of our particle physics work: the energy frontier, the intensity frontier, and the cosmic frontier. Now, you've heard a little bit about the theory, and my colleague after me will talk a little bit about the cosmic frontier, but I want to just bring you up to date a little bit on what we call the energy frontier, which is essentially the highest energy attainable by experimental equipment that we have, and then the intensity frontier, which is the highest intensity particles that we have to look for very rare occurrences in science. The history of the universe tells you essentially that the Big Bang happened at some point, and we produced essentially all the components that were associated with the things that we now see in the universe. What we do with our particle accelerators are to go back in time effectively by going to higher and higher energies, to energies that are very close to the beginning of the Big Bang. And by doing that, we can get more of the details about the constituents of science, and particularly about the constituents and the laws of science and laws of physics that actually govern how those constituents interact. Just to give you a sense, not everybody in the audience has a sense of essentially how small and how large we are actually dealing with things in our universe. In this particular presentation, you see essentially this factor of 10, a factor of 100, going from essentially a flower right down to the structure that we actually need to be able to see some of the things that make up all of the subconstituents of that flower. And at each one of the stages, we effectively start looking at using our instruments are effectively microscopes. Well, this is a smaller instrument that allows us to see things that we couldn't see with our naked eye, and going to microscopes and then to electron microscopes, X-ray machines, and ultimately, of course, to particle accelerators. Because if you want to look inside of the atom, which is a very small object, you need to have a particle accelerator to do that. I wanted to just give you this particular slide, not for any of the information on it, but except for the time frame. I wanted to make a case that we should understand that basic science that we do can happen over a long period of time. And what you should look at in this particular great moments in physics, of course this is my own point of view, is that sometimes you get 100 years that happen between the kind of fundamental knowledge that we actually get today and the fundamental knowledge that might be applied to some solution to a problem that we might have 50 years from now or 100 years from now. This slide, at least as far as I'm concerned, is the true motivation for why we do our academically motivated work. We need to be able to understand things now because the problems that we will have in the future, in fact the problems we have now that we don't know about, may in fact depend upon the knowledge that we gain in doing the science. The Standard Model is a model of the most fundamental constituents that we have. Our current best knowledge that we know about in particle physics, the Standard Model includes matter particles, forces that interact between these matter particles, and the force carriers that actually are exchanged between those particles. These are essentially the families of quarks and gluons and leptons. Each one of these particular columns here corresponds to essentially a combination of individual particles that, when mixed and matched, can produce some of the more complex particles that we have that make up the atomic structure. Now, there is one little small problem, and that is we're not quite sure how these particles get their mass. And that is one of the most motivated experiments that are going on now throughout the world. And that is to look for a particle that might actually help in terms of being able to understand why some particles are very large and some particles have essentially a light mass. And that is the coupling to this particle known as the Higgs, which is a particle that is being searched for at this very moment at Fermi Laboratory outside of Chicago and at the Large Hadron Collider in Europe. We will actually talk a little bit about accelerators, and we're not satisfied with the Standard Model because we can't satisfy some of these equations. Now, I said to a group of students that we met with earlier today about accelerators. One young person asked me, what are accelerators and what's the smallest accelerator? But I hope they're in the audience, I wanted to show essentially that this accelerator you can hold in your hand. And this is one of the first cyclotrons that were actually produced by Lawrence. And it's 4.5 inches in 1929 to 1930. Now, our accelerators have gotten somewhat larger since then. This is Lawrence at the 27-inch cyclotron. And I was happy during my career to actually work on a cyclotron at Michigan State University, where I really got interested a lot more in this material. And in our country, we have the Large Accelerator. This is the Fermi National Accelerator Laboratory, which is a Department of Energy Office of Science machine. We have been in operation since 1972, and we started our laboratory in 1968. We're characterized by a number of clustered accelerators. We pass the particle beams from one accelerator to the next as we go to higher and higher energies. I just wanted to show you this overview of the laboratory. It's a 4-mile circumference main accelerator, a superconducting machine, and also a 2-mile circumference injector machine that is used to pass the particles from this machine to that one. We do particle accelerator physics in 2 ways: with a fixed target machine, that is to take a particle beam, hit a stationary target, and produce secondary particles that we study, and also to produce matter and antimatter colliding beams within the Tevatron experimental systems. Here is essentially what we have in terms of the upgrades of the particle beams from the electrostatic accelerator, where we start the particles off, and also a series of accelerators that increases the energy of the particle and then pass them to the next machine. This is a linear accelerator known as a LINAC. It's 400 million electron volts. I should point out, of course, that this is a one-pass accelerator, which means that the particles start at one end at 750,000 electron volts, and at the other end they come out at 400 million electron volts. I should point out also that some future accelerators, like the International Linear Collider, will in fact be a series of these type of linear accelerators that actually pass through one series of acceleration cycles. When you leave essentially the area of going to a higher energy, you have to go to an area of cyclic machines. This is a booster, which is 8 billion electron volts, which means that the particles go around in a circle, and then the main injector, the production of antimatter, which is antiproton source, and then a superconducting accelerator that uses superconducting material to produce a 1 trillion electron volt machine. I had some animations that shows you essentially how we actually do stationary acceleration interactions and also colliding beams, but given the limited amount of time I have, I'm just going to just pass that up. How do we see particles? To determine what happens in the collision, we measure the direction, the charges, and the energies of the particle, and we use a number of tracking devices and calorimeters to essentially identify all the particles that went into the interaction, as well as all the particles that actually are produced as a result of the interaction. The human eye, for example, is one of the detectors that you probably carry around with you all the time. The scanning electron microscope shows essentially these retinal photoreceptors, and in fact, some parts of these systems can also not only distinguish a single photon, but also can distinguish color. Ionization is one of those properties that allow us essentially to track particles as they go through materials. The particles that go through leave essentially these ionization tracks, and by looking at those tracks, we can tell where the particle has been. We can tell essentially how much charge the particle have, and as we go through a magnetic field, we can tell the charge of the particle. Some practical things associated with some of these detectors are ionization smoke detectors, as well as a number of things associated with detection. One of the things that we wanted to point out, of course, Mr. Einstein got his Nobel Prize for the photoelectric effect, which is one of the basic type of mechanisms that we use in photoelectric detectors at our high energy physics experiment. I will show you this animation. This is an animation that actually shows you essentially how we actually collide particles. The expectation, and should be important, this is for matter and antimatter collisions, but it's also true for particle collisions. The particles usually pass through each other, but every once in a while, one might in fact actually hit another and produce these secondary events that we actually use to essentially find new particles. The difference between the fixed target experiments and the colliding beams experiments is that the colliding beams experiments have twice as much energy. The energy frontier, the Large Hadron Collider and the Tevatron, are in fact two types of cyclic accelerators that produces large amounts of energy, and the Large Hadron Collider will, when it reaches its full intensity, be about 7 times the energy that we have at Fermilab. One of the things that we do with the energy frontier, of course, is train new scientists and develop new techniques. And as you go to higher and higher energies, you get new things that come into play and things that actually keep you from essentially doing the experiments in a simpler way. The energy frontier of the Tevatron, which is the large accelerator that we have at Fermilab, provides opportunities. Perhaps we're still searching for the Higgs boson at Fermilab. We produce a number of PhD students and graduates, and we have great operational capabilities because of the high intensity that we have at our laboratory. I'm pointing out here the two large colliding beams detectors. This is the CDF detector, and this is the D0 detector. These are two machines that we actually have. And I want to point out also that we're very international in terms of the kind of experimental work that we do. It includes essentially large collaborations with nation-state contributions and numbers of scientists from around the world. There are a number of open questions in particle physics, and I want to end by talking about some of these questions. And I'm going to leave them as questions because some of the things that I think my colleague will talk about will tell you essentially some of the experiments that are being planned. Not those that are necessarily being planned for accelerator-based science, but also the connection between what we do at accelerator-based science and those things that we do essentially with astroparticle physics. There are many types of elementary particles, and we want to find out if particles such as quarks and leptons have substructure. The only way to do this, of course, is to increase the energy of our accelerators to higher and higher energies so that we can probe deeper and deeper into these particles. The Large Hadron Collider in Geneva, Switzerland is a 27-kilometer circumference accelerator, and it's approximately 150 to 50 meters below the surface. These are some of the detectors. They're very large detectors. I didn't give you a sense of the size of the detectors that we have at Fermilab or the Large Hadron Collider. The two detectors I showed you at Fermilab are 5,000 tons each. The detectors that you see here at the CMS detector, at the Atlas detector, are 7,000 tons each. These are very complicated machines. They're some of the biggest and more complicated machines that human beings have built in the world. This gives you a chance to see what the size of one of these, and this is a regular sized person. And here is essentially the CMS, the Atlas detector, before it actually was completed and closed up. the operation of that accelerator, and I know you may have some questions about this later, but the operation of that accelerator is complete now. They are actually engaged at 3.5 trillion electron volts for proton-proton collisions. This is not the maximum energy they hope to design to get to, but it turns out that right now they're operating at this particular level and doing it somewhat successfully. These are the detectors that they use. But I wanted to also end by talking about what the future of Fermilab might be. Since we do not have the energy frontier, I told you about the intensity frontier. And that requires us essentially to build essentially new types of experiments and also to improve our accelerator system so that we can have high-intensity experiments. Two of the high-intensity experiments that we have are experiments that actually produce neutrinos, which is one of those type of fundamental particles, and to look at the oscillation of these neutrinos at detectors that are near the laboratory and also at facilities that are away from the laboratory. This particular beamline and this experiment is operating now. The Minos part of that experiment is operating in the Sudan mine in Minnesota, and a new detector is being built near that particular area to take advantage of the neutrino particles that travel from our laboratory to that laboratory. We're trying to see, in fact, if these are particles of the same sort. That is, the three types of neutrinos that I showed before may, in fact, be associated with the oscillation of one of those neutrinos into another, and therefore just the same species, but a different flavor of those same particles. We are thinking also about putting together a Project X, which we proposed to the Energy Department, to produce high-intensity particles that will actually fuel the neutrino program, as well as long baseline experimental program for a much longer baseline neutrino project. Some of this future planning for the laboratory also leads us, and I'm finished now, leads us to the question of why we do this work and how, in fact, it can benefit our country and benefit the world. I only point out just a few things, and I could make a whole 45-minute list of things that actually come out of high-energy particle physics. But our original director had the idea of using part of the linear accelerator to do neutron therapy facility, which we've been doing at Fermilab since the mid-1970s. Proton accelerators for medicine. We had the production of a proton machine at the Loma Linda facility in California, as well as positron emission tomography systems that are around the world. We also produce superconducting wire for our Tevatron, essentially creating a new industry because practically this particular type of material was not available to produce our magnets, so we produced it ourselves. And it was mentioned earlier today that certainly the transfer of information from CERN to various places in the United States back in the mid-1990s created essentially the World Wide Web. This came out of high-energy particle physics. But I just want to end talking about positron emission tomography because people always ask me a question working on one of my experiments studying CP violation, what's the value of antimatter? Well, the P in PET scans is positron emission tomography, and the positron is the antimatter particle of the electron. So antimatter effectively can save your life. I like to say that, and people always want to have a much deeper discussion about that, and I'm happy to do that. So I wanted to just point out that we continue to smash atoms and nuclei to make up our universe, and every day we learn something new. And by doing these particular type of studies, developing the detectors, developing the accelerators, we're able to actually push our technology to a point where we can find some of the solutions to questions that we have now, and hopefully solutions to questions that we don't know we have now. Thank you.
Okay, we'll try one more time to get PowerPoint to do the right thing for us. Good evening. Let me add my thanks to those of Dr. White and Dr. Gates to the Carnegie Institute for inviting us to come and talk to you today. And I have to tell you that Herman is the certainly happiest person in the room that he's able to come tonight. I'm the second happiest because I would have to cover his talk otherwise. And I always opt for if it's possible, for the last position because I get the easiest job, which is I get to explain the whole universe to you in the 15 minutes that remains. And that turns out to be the easiest job because, of course, to a physicist, the universe is actually a pretty simple thing. It starts with the fact that we've already talked about physics on the very smallest scales. And what I'm going to do is to combine that with what we now know on the very small scales also applies to the history of the universe, which determines the physics that we see on the very largest scales. So if physics is supposed to be the science of everything, there should be some connection between the very large and the very small, because, of course, if we explain what everything is made of, how it connects together, we've got at least the makings of a picture that actually determines what physical reality is at whatever level you choose to describe it. That is, we can't explain, for example, how chemistry and life emerges from constituent parts like atoms and molecules, but we can at least understand where the atoms and molecules came from. So any story that you want to make about how you come up with a reality like the one that we see has to begin with understanding physics at the very fundamental scales. So the two sciences that have combined most recently are particle physics and cosmology and astrophysics. These are, as described here, involved with understanding the nature of matter, energy, space, and time at the most fundamental level, particle physics, and then the evolution and the fate of the universe, how it's affected by the basic constituents of matter and energy, and the behavior of space and time. Now, part of understanding how that applies to the very large is understanding the nature of space and time itself. And that begins for us in around 1915, 1916 with Einstein, who gave us a new view of gravity. And it might seem like a strange place if you want to understand space and time to talk about gravity to begin with. But it actually is very relevant because in order to understand gravity, which was something that Einstein was very much driven to do, he was actually forced by the same kind of mathematics that Dr. Gates described to you earlier, to actually say that gravity had to have some fundamental connection to the properties of space and time together, which we now describe as space-time. And the way that connection works is that space-time has to be something that isn't just a background upon which matter and energy play their games. It's actually true that the matter and energy and space-time itself all have to be active participants in the same game. It's a profoundly different picture of the universe that came in 1915 than we'd ever had before. And in some sense, it's a more complicated one, but it's also one that gives us an opportunity that could not have been realized otherwise. Which is to say that if we want to understand the universe on very large scales, we have to deal with a very fundamental problem, which is that we're stuck here on Earth, at least most of us. And therefore, if we're going to do any kind of examination on the very large scale, we don't have direct experimental evidence of what's happening in another part of the universe other than the little corner that we happen to live in. Now, we can see, for example, stars and galaxies and supernovas and explosions that happen very far out, but we can't actually do direct experiments with them. And we also can't look very far back in time until we have some understanding of what physics is actually evolving or causing to be the picture of evolution for the universe. And what Einstein has done by saying that space-time itself is an active participant is he's given us a way to examine parts of the universe that we otherwise would not be able to see. And what I want to do is to spend about 10 minutes or so trying to describe to you a little bit about how that works. Now, when I say can't see directly, what I really mean is that we now understand that there are things in the universe, from experiments that we can do here on Earth, which we have no direct knowledge of, or at least did not have any direct knowledge of, previously to about 10, 12 years ago. And the reason why we know that that's true is because since about 1930 or so, it's been the case that we've taken Einstein's theory, which says that space and time have a shape, and that that shape is determined by the gravity, and that the gravity comes from the matter and energy that's contained within that space. And that geometry tells us that, in fact, we can't account for all of the gravity by looking at all of the things that we see in our telescopes when we look far out into space. In short, all forms of matter and energy that we know about create gravity, and that gravity changes the shape of space and time. And by therefore looking at what happens to light when it goes through a region of the galaxy where gravity has bent or changed the shape of space-time, we can get a determination of how much matter and energy is in the region between the things that are producing the light that we see in the telescope and us, where we receive the light. So in short, gravity bends light very much like a lens from a pair of eyeglasses. And what that means is that if you have a set of things, a target in the background, as we do here with these colored balls, and they produce light, if there's anything that's between these guys and us, any form of matter or any form of energy, whether we can see that or not, we can see its effect, because the gravity from that actually distorts the picture. Instead of this, what we see is something that has objects strangely shaped, warped, and therefore even invisible stuff can't hide. So what Einstein has done is to say that there might be parts of the universe, forms of matter, forms of energy, which we can't see directly here on Earth. We don't have the kind of instruments that could make them visible, or we just haven't looked for these things. And yet when we look out in space, we can see evidence for their existence if we can't account for all the gravity with the things that we see in front of this picture. Okay? So we can make even invisible stuff visible. Now, over the last 10 or 15 years, we've in fact, with other results from other kinds of experiments we can do, been doing these observations to try and account for all of the matter and energy that we see. Is in fact the gravity that we actually are able to measure going to be consistent with all of the gravity we expect from all the stuff here, all the shiny things here? Now, we know that normal matter exists as far as we can see, but in fact, what we find is that the amount of gravity that's produced is so much larger than what we can account for by adding up what we should expect from all of this stuff, that in fact, only about 5% of the gravity is actually accounted for, which is a pretty shocking thing, right? It says that most of the universe that we've been studying for centuries has, in fact, been invisible to us. The gravity that we actually see distorting the picture of galaxies in the background actually indicates to us that there's a lot of invisible stuff. Well, that's not so good a story unless you're an experimentalist, because it means we now have something to look for. And the very first thing the experimentalist or the theorist gets to do is to give it a name. Now, there was a time when physicists were actually pretty creative at coming up with names. Since then, we've gotten a little more prosaic. And so the very exciting name dark matter was given to particles of matter, which we think might be responsible for some of this gravity. And in fact, the dark matter, as we call it, has to be something that we now know, again, from other experiments that we can do, but mostly from experiments and observations of this gravity in space, has to be very different than any other form of matter that we've ever seen in the laboratory. First of all, there's got to be a lot of it around, right? Much, much more. In fact, when we do the correct accounting for it as accurately as we can, what we find is that in this room, all of the stuff that you're made of, the seats that you're sitting on, the air in the room, the floor, the ceilings, the walls, if we add up all of that in the universe, that accounts for about 0.5% of the actual amount of matter that's, of gravity that's responsible for the distortion of the background view that we see. So that means that we are actually just a tiny correction on the amount of matter that's actually out there. And it also says, pretty dramatically, that in this room right now, there's lots and lots of dark matter. Does it tickle? Okay. Well, probably not. And the reason is because we don't have any instruments right now that are actually sensitive enough to see it, even though there's so much of it flowing through the room right at this moment, going right through your body. But we don't actually have any way of knowing about it except for gravity that it causes. So the study of dark matter in the universe is something that we have to use the universe as the laboratory for study for right now. And we'd like to change that, because even though that tells us about the existence and allows us to know some of its properties, it's still not enough for the experimentalists. What we'd like to do is to be able to make it in the laboratory and detect it in a way that allows us to play around with it directly. And so what we hope to do in the future is exactly that. But in the meantime, before we get to that point, there's an even bigger problem, which is that some of the gravity appears to do something that's rather strange, even for something as strange as dark matter, which is that when Dr. Gates showed you that equation, I'm sure that many of you in the audience spotted this rather curious part of it, which is that it actually allows for anti-gravity. He didn't talk about that. It's one of these things that we kind of kept in the background. Theorists sort of kept it to themselves. Even many experimentalists who've taken general relativity weren't often asked to think about the fact that in general relativity, it's actually possible to have something called anti-gravity. It means that if I throw an object into the air, instead of coming back down to my hand the way it's supposed to, it can actually keep speeding up, going all the way away from us, out forever as far as we know. Now, the only way that we can have that is, of course, if we have some form of matter and energy which is different than the matter and energy that we're normally used to. And physicists give that a very technical term, a very technical name as well. It's called exotic, okay? And this turns out to be the reason why you probably haven't heard of it, right? Because exotic things for scientists or for normal people are usually things that you don't mention in polite company. Right? You only talk about it amongst yourselves in corners of the room where you're not sure, where you're pretty sure that nobody else is going to overhear you. But it is the case that if there's such a thing as exotic mass energy, it can have anti-gravity. Now, one of the things is, of course, now that we know how to look for things that we haven't seen in the laboratory, we can ask, does such stuff exist? And the answer is, well, if it does, it would have very strange properties in terms of the history of the universe development. Because, again, all forms of gravity affect matter and energy, but matter and energy also affect how much gravity is out there. So the two are coupled. So the history of the universe, in fact, is tied to whether or not this stuff exists or not. And in fact, when we look at the history of the universe's expansion, that is how it gets bigger over time, in fact, we see clear evidence that, in fact, dark energy or exotic energy does exist. And the way in which we see it is that we have the Big Bang, as was described to you by Dr. Gates. The universe comes out of this explosion, and because of all of the gravity of all the matter and energy that's created at the time of the Big Bang, the expansion should be slowing down over time. And in fact, it did for the first few billion years, but roughly 5 to 7 billion years ago, we saw something very strange, a kink in the curve, which means that, in fact, the universe's expansion is speeding up. And that's exactly the case in which you throw something into the air, instead of coming back to your hand, it keeps going up. It's getting away faster and faster, which means that you must have some form of anti-gravity or something that gives an effect very, very similar to it. Now, why would you want to know? Well, it could be that every once in a while you think to yourself, I wonder how the universe is going to end, or will it ever end? And to know the answer to that question, we have to know something about this exotic mass energy, because it gives us drastically different predictions for what the end of the universe will be depending on its properties. We could either go to a case in which the effect dies off, and so we continue to get bigger and bigger for the universe, but in fact it just keeps getting bigger and bigger forever. Or perhaps something strange happens and it changes over to something that's attractive and the universe collapses in on itself. Not too much fun for us. But even worse is if, in fact, the effect gets even stronger over time, which means that over some period of billions of years, the universe starts to expand faster and faster, and in fact, at some point gets to be so fast that matter itself, the regular matter, is no longer stable. So how do we study this, dark matter and dark energy? Well, the first is we'd like to be able to make dark matter in the laboratory, and that's one of the goals that we hope that the Large Hadron Collider will achieve at some point. But we can also look for dark matter in the universe. We can do very sensitive experiments deep underground. So Dr. White didn't mention it, but in fact there is a plan, not yet enacted as something that we're definitely going to do, but something that we hope will be done, is to build a very deep underground laboratory that's very sensitive to forms of matter which we can't detect at the surface because there's too much interference from all the regular forms of matter energy that we know about. But we can also look further out into space more and more accurately. So we can do that with large ground-based telescopes, or we can do it with large space-based telescopes. Both of those have the characteristic that what they intend to do is to take very wide field pictures of the sky. That is to look at a large chunk of the universe all at once and very, very deep, so that you can cover most of the sky, that is, look at most of the universe all at once in order to do some of these very sensitive studies of the effect of gravity. And if it exists in the way that we think, we can actually study the effect of anti-gravity over a period of time in the universe's history. Now, there's a number of experiments that people are talking about because the experiments themselves are intrinsically interesting. And this is one of them, the Dark Energy Survey. This is a prototype telescope that will be installed at Chile, is being installed at Chile this year, and will be seeing first light towards the end of 2011. And the Europeans also, of course, are in the game. And so they are looking at designs for space-based telescope, again, to look for, explicitly for the effects of dark energy and dark matter in terms of the gravity. Now I'm going to end with a statement here, which is that the whole idea for doing physics, as Dr. White says, is that we find it fun and interesting, but it's also the case that it can predict certain problems that you might come up with in the future. It can also be the answer to questions that you don't even know to ask yet, or the solution to problems that you don't know you're going to have. But there's an important reason for physicists to do that, to do this kind of work, which is there are fundamental challenges if we ask questions, what is the universe made of? To understand that fully 95% of it wasn't even known until 12 years ago is a shocking thing. It's an embarrassing thing. It's probably not something I should be telling you in public. But in fact, we're not going to get to the answer for any of these questions until we actually make some fundamental advancements in actually determining, first of all, what are the fundamental constituents. We used to think that they were atoms, and that atoms were formed of this periodic table that Herman showed you, of quarks and electrons and so forth, and we find that that's, in fact, a very small percent, maybe only about 5% or so of what the universe is actually made of. So, in fact, what we've got are fundamental questions, and that's the best place for a physicist to be, because it means the future, even though it's dark, is awfully bright. Thank you.
Well, in 45 minutes, we've covered most of modern physics. That's rather remarkable. We do have time for some questions. There are microphones in either aisle, and I'll invite those who have some questions for our three speakers to come to the microphone. Please.
Thank you for this, a very interesting talk. The saying that 95% of the universe is stuff we don't know anything about is very dramatic. And so I'm wondering, but it seems like that comes out of the equations side. And so I'm wondering, how sensitive are those equations? Are there small changes that make it 40% of the universe's dark energy or matter rather than 95? I come at this very much as a novice, and a few podcasts here and there, but I've heard a few things saying like changes in our understanding of the geometry of the universe make dramatic changes into how much dark matter there would be.
Well, I would say that, in fact, we didn't have time to go through it here, but there are lots and lots of cross-checks that you can do. So it isn't just equations. There's lots of pieces of evidence which we've been gathering since really around 1930, 1932 or so, which indicate that we were not able to account for all the gravity that seems to be around there. In fact, even our own Milky Way shouldn't really be stable in the shape that it has, because there's simply not enough normal matter, which is mostly hydrogen and helium, to explain how it's able to rotate as rapidly as it does without flying apart. So there's a number of things which actually don't hang together unless we assume that there are sources of gravity other than those that come from the usual accounting of what we can see in our telescopes. Now, is it 95% or is it 93% or is it 97%? We think we know pretty well that it's within a pretty small range of a very large number, but it's certainly not going to be, 2 years from now we discover that it's only 75%. In fact, dark energy and dark matter are primary constituents of the universe at a very large level, and it's very hard to get around the chain of evidence that actually shows that that's the case.
Please.
I'm just going to be the devil's advocate here and bring up negative matter.
That'll be your question.
You mentioned dark energy and how due to dark energy, if dark energy were playing a role on a ball I was holding and I tossed it up in the air to continue accelerating, would is that in any way similar to negative matter?
Well, maybe you mean negative mass. So one of the ways in which you can have something exotic is that it's got a mass that somehow gives negative gravity or anti-gravity or repulsive gravity. Nobody's ever seen any example of such things or know how you would make it. And I would say that, as a way of answering the question, exotic, anything that sort of has this title exotic in it is something that's highly speculative. There might be some ideas about equations that people like Dr. Gates would write down, which give you some indication that perhaps under certain situations you could have something described as negative mass. But in fact, experimentally, nobody has any evidence for how to create it in the laboratory or how to study it directly. We simply see the effect on the universe as a whole, right? So this is something that we're all novices about. Nobody's going to be able to very quickly come up with a way of explaining, it's obviously, it's easy, it's in the equations that we already have, and we believe those equations.
If I could just add a bit, if you believe in string theory, then the idea of negative mass square objects, in fact, is an anathema to the mathematics. It's actually inconsistent. But who would believe a string theorist?
Please.
Thank you, gentlemen all. I'm going to ask this question two different ways. I know it's much too much than you can answer here, but anyway. What can M theory explain that other theories cannot explain, and what cannot M theory explain? Or what are the advantages of M theory as versus other theories, and what are its disadvantages? Okay.
I think maybe the theorist might answer that.
By first explaining what M theory is.
Sure. In a much longer talk, I actually do talk about M theory, which is this idea that is a step beyond string theory. The one thing that we can say about M theory is that the M stands for mysterious. We also can make some observations. When you look at string theory, from some point of view, it looks like there are 5 different theories. But in fact, if this thing, M theory, exists, then there's only one theory. And that would be philosophically a good thing, because if you claim that string theory is a theory of everything, then why are there 5 everythings? So, it's that as a philosophical issue. In terms of the actual understanding of M theory, it is still, and it's now, we're about 15 years past the initial suggestions of it, it is still a very little understood concept in theoretical physics. And so if there are some young people in the audience, like the young man who just asked this question, there's work out there to be done.
Please.
Yes, my question revolves around the Higgs boson. If physicists are unable to find the Higgs boson, is there a plan B?
Can I take that? You want to do it? You want to do it, or you want me to do it?
I think you should do that. Well, I know the plan A. I can tell you the plan A, and the plan A effectively is the hunt for a light mass Higgs at the Fermi National Accelerator Laboratory, which is focused there because we have a limited amount of energy. For a heavy mass Higgs and for even a light mass Higgs at the Large Hadron Collider, they are actually looking essentially for a particular type of particle that actually matches the theory as it exists now. So with these two accelerator systems, you can essentially cover a fairly broad range of the possibility of identifying this particle with the optimization of the detectors that are produced both here in the United States and in Europe. That's plan A. And given enough time and enough energy, and particularly enough running time between the work that we do here in our country and the work we'll do over in Europe, we should be able to essentially either find this particle or exclude it. Now, plan B.
There's a very famous story about a theoretical physicist and one of his experimental colleagues. So one day the experimental colleague runs into the theorist's office and says, "We have data showing this," and he then shows some plots, to which the theorist replies, "Oh yes, that's perfectly predictable because we have this theory here," and then he brings out, his calculations. But then the experimental colleague realizes that he showed his plots upside down to the theorist. And so he says, "Oh, wait a minute, I have to turn it this way to accurately show it to you," to which the theorist says, "Oh, yes, we have a theory." So, in fact, there is a plan B that has been discussed off and on for since I was in graduate school in the 70s. And it's an idea of that the Higgs itself is not a fundamental particle, and that, in fact, there's something that are called composite models. And in these composite models, you then try to construct the Higgs from something that's deeper inside of it. So there is, in fact, a plan B. There's always a plan B for theorists.
My quick preliminary question for the string theorist: when or will you come out with a sequel to The Elegant Universe?
I'm sorry, say again?
Will you come out with a sequel to The Elegant Universe DVD?
Well, first of all, I'm not Brian Greene, as some of you might imagine. Brian, in fact, has released two sequels. There is The Fabric of Space, which was released, 4 or 5 years ago. And then right now he has a new book with the word cave in the title. I don't remember the exact title. So the books are out there. With regard to the video, if that's what you were referring, there is, in fact, a sequel video that is in post-production right now. It's being done again by Nova and the GBH crew in Boston. Brian will again be leading a motley assortment of physicists as we try to tell the story about what was left out of the first one. And if it is released on schedule, it'll probably be out there in the public perhaps in November this year. And I'm one of those motley crew.
All right, I thought so. My real question is the ratio of dark energy to gravity, I understand, must be accurate up to 10 to the 120th or something. First of all, is there truth to that, some basis for that, and what are the implications of that as far as an initial condition goes?
You're clearly not a physicist, but you are clearly determined to embarrass the entire discipline.
Okay, so to succinctly try and answer the question, we start from a belief that general relativity is correct. There's lots of evidence that the basic principles of it are correct and that the actual predictions of it are correct, right? Your GPS system that navigates you home depends on general relativistic equations being correct. So there's a lot of reason to expect that it's correct, but there are still some aspects of it for which it might be wrong. Theorists look for places where they might be able to modify the equations in some way to get slightly different effects for gravity in ways which don't violate the experiments that have already been done. So if we take that as a given, that it's correct, then that lambda, the symbol that Dr. Gates pointed to, does have a natural place within quantum physics, which is that it's the effect that one gets, which is in fact anti-gravity, from all of these things that happen at levels so small that and so fast that we can't actually see them with any of our experiments, called virtual processes, in which you have matter and energy basically popping off all the time. The net effect of that in general relativity is, in fact, to give you repulsive gravity. However, the naive assumption as to calculating how large that effect should be is what gives you in some ways in which you do the calculation, right? It's not in every way that you can do it, but in some ways in which you do the calculation, that's what gives you this being off by 10 to the 120, right? If that were true, in fact, the universe wouldn't exist. It would have blown itself apart within the first few microseconds of the Big Bang. So we take it that we exist is something that has to be absolutely true for every physics theory, right? So we have to sort of reject the fact that that lambda term is due to simple quantum processes and nothing else, because that gives you, as you say, the wrong answer. But once you say plus something else, then the plus something else has lots and lots of different theories that people can say, well, I can add this, and I can add this, and I can add this, or I can add that, I can add that. And any number of those can modify the quantum processes that we know about, that we know happen, in such ways to just happen to give you the right answer, which is the amount of expansion we see today. But of course, are any of those correct? Well, again, you have to be able to do experiments that are accurate enough to probe at that level. And in fact, that's what the next generation, we hope, is going to be able to do.
And forgive me if you are a physicist. I spoke in haste.
That's a look.
Yes, the look.
Okay. 2 more questions, please.
Well, first of all, if there's a possibility for funding, there's always a plan B. But what I wanted to ask about is if so much of our thinking is established in the concept of matter, and so much of the universe is not matter, aren't we sort of captured in our terminology, even the 3-4 dimensions that we talk about, aren't they just terms of convenience of the moment, so to speak, and that it's sort of like the Earth, we thought it was flat, and that worked for a while, and it got us where we had to go. Aren't we sort of at another stage of that kind of, and we're still captured by our old way of conceptualizing everything?
Well, everything seems to be in the same structure. There's matter, energy, space, and time, and that's pretty much the bottom line for most of the things that we actually work on and study in particle physics. Now, if you say the matter that we can actually see, when we talk about the universe and the 5% or so, has to do with essentially the way in which that matter actually interacts and produces things that allow us to know that it's there. But as Dr. Gladney said, there is some matter that doesn't have that luminous capability. The fact that it doesn't actually produces characteristics that we can see doesn't mean that it's any less accurate or any less valid. The fact that it doesn't have a luminous characteristic means that it still, in fact, will interact with matter that we can see in very much the same way. The study of matter itself, or the study of particles, the study of materials themselves, are basically a study of characteristics. And sometimes we study those characteristics to distinguish one piece of matter from another piece of matter. The fact that dark matter and luminous matter are just 2 types of words that we attach to these matters doesn't change the fact that the basic structure and the basic laws of nature that we actually work on will apply to both of them.
I don't see how we know that for sure.
Well, that's knowing for sure is based upon the fact that science, and particularly physics, considers sure to be reproducible observation. Once we do an experiment, we will continue to do that experiment. Sometimes our colliding experiments at Fermilab and at the Large Hadron Collider are 10 million events per second. So we do things over and over and over and over again. Every time we get the same answer, we characterize that as being sure. When we get something that is contrary to that, or what some people will call a discontinuous variation, then we will actually go back into the laboratory, go back to our theoretical colleagues and say, we've learned something new. And that's basically how we actually go from step 1 to step 2.
Yeah, it is always the case that in science, it's a petitioning of nature asking the simple question, how valid is this? And within the context of my limited human capabilities. That's always what science is about.
I'm going to give the youngest member of the audience the last question this evening.
Actually, the guy over there, he's probably younger than me.
Okay, sorry.
Well, I've heard talk about how different universes might be possible, such as antimatter universes. Could a dark energy or dark matter universe exist? And if so, what would it look like?
Well, an interesting question, of course. So if I were to take Dr. Gates's string theory seriously, start from that.
Excuse me. I think the appropriate response is, does it take you seriously?
Both are valid points of view. Within string theory, there are a group of very prominent, very active, and very distinguished physicists who believe that string theory actually predicts that there should be many, many, many universes. In fact, something like 10 to the 500, right? 1 followed by 500, 0 possible universes out there. We can't see them. They're all beyond what we call our horizon, but they're there nonetheless. And in some of those, in fact, many of those, the dark energy is much, much larger than it is in our universe. There's no matter at all. It's all wiped out. And we happen to be one of those very, very rare universes where there's a close balance between the amount of dark energy, dark matter, and normal matter, such that we are allowed to exist. Now, I think any theory that says we have to ask for permission to exist needs some questioning. But if you're a string theorist, you can find some arguments like this to be very convincing. And those, in that sense, you do involve other dimensions, alternate universes, very different from our own.
And I'm going to play the devil's advocate here. Because, in fact, your question about other universes also is one possible explanation for why we don't live in an eternally inflating universe here. The idea is that inflation, this period at the very beginning when the universe undergoes its rapid growth, a real puzzle for physics, and forget about string theory, so let's pretend we're real physicists here. If you forget about string theory, what's called the graceful exit problem from cosmology is a very, very tricky thing to negotiate. And the idea of internal inflation can be divorced totally from string theory and proposed as a possible explanation for how the graceful exit from inflation actually works. So it's a little bit more broad than string theory.
Jim, Larry, Herman, thank you very much. You provided us with a wonderful evening. Thank you all for joining us. We're now adjourned.